Good morning, and welcome to the second day of Virtual NANOG 79, coming to you live from the entire world. I'd like to welcome you. My name is Alex. I'll be your host this morning. A couple of quick things before we start. There's a Women in Technology lunch, virtual. It's on the agenda. Please don't forget the virtual expo. Fill out the daily surveys. We're going to be doing a special survey during the presentation today to see what you want to have as BOF breakouts later in the conference. Stay tuned for that. Then, without further ado, Mr. Tom Daly, an advisor at Fastly, with Tuesday's keynote.
Thanks, Alex. Good morning, everyone. If you're west of Boston, and good afternoon, everyone. If you're east of Boston, it's a pleasure and an honor to be here. During this keynote, I am hopefully going to convince you that certain aspects of our network are becoming disconnected, and we may or may not realize it. If you want to shoot me comments afterwards, my email address is below. It's tjd@q7.io. A tiny bit of housekeeping to start, which is some acknowledgments for engineers around the world that helped contribute to this presentation. Throughout the presentation, the perspective will be through that of a operator that is building content delivery and edge compute. And while the perspective comes from my work at Fastly, the views in this talk don't necessarily reflect the viewpoints of Fastly. So there are some major technological themes that are going on as networks are being built around the world today. We're all trying to deal with scale as traffic and volume through the network grows, as we saw from Craig Labovitz's talk yesterday and the COVID-19 pandemic. We are all trying to build resilient and available networks that are agile and reconfigurable to our customers' needs. Everything needs to be private and secure. There's just too much work to do, and the networks are too big today, so we have to rely on automation as a means to get our jobs done. And we want to think of our networks today as infrastructure as code, so that way that automation work can be done. All of this is being done with a mind towards simplicity, because the networks of today, whether they be in the data center, across the interdomain routing fabric, or down into the user bases, have just gotten too complex for any one single human being to reason about. And therefore, the simpler and more repeatable that they can be, the better off we are in operating them. And all of this comes from many, many cycles of innovation in those networks and how we tend to operate networks today. Innovation is really important because it allows us to react to changes, discover new opportunities. It allows network operators to create competitive advantage. It allows us to scale delivery, drive efficiency. And in some cases, that cycle of innovation allows us to attract top talent to our companies, so that way people want to come and work for us. Innovation isn't always planned, though. Serendipity, in many cases, leads the way in terms of inventing some of the greatest things that have come to be on the internet, such as being able to host NANOG virtually. So I want to talk about innovation cycles as part of this talk today, and then try to convince you that we're missing a piece of the innovation cycle. And in order to do that, I'm going to shift back to the 1900s and an article from Telephone magazine in August 1900, which is For Sale Cheap, a 110 drop standard telephone and electric company switchboard in good order. Can be delivered by September 15th from the T-Bray Telephone Company in Washington. This 110-line telephone operated switchboard gave us 110 lines at 9.6 kilobits per second, or just under 1 megabit per second of voice switching capacity. And this was the manual plugboard type switches, and really was the advent of the switching technology that we know and appreciate today. But how did we jump into automated switching? Well, along comes a gentleman by the name of Almond Stroger. And it turns out that Stroger was an undertaker. Stroger also had a competitor across town. And the rumor mill, or the conspiracy theory says that Stroger's competitor, his spouse, was a telephone operator. And she was actively diverting calls away from Stroger's business to her husband. And so Stroger became very frustrated by this and decided to invent the first automated telephone switch called the Stroger step-by-step switch. This technology, the intellectual property, was purchased by General Electric and was used to build some of the very first automated telephone switching COs that we know today. And so, roughly over 120 years, even 140 years of innovation, we go from the manual switchboard to the step-by-step switch, eventually to the crossbar analog switch, which became the basis for the common control platforms that we see in chassis-based routers and switches today, all the way up to the automatic digital switches that we knew of the late 70s and into the late 90s. These are the equivalent of our BFRs, our big chassis type devices that we've seen in the IP world. And then in the late 90s, with the advent of soft switches and voice over IP technology, this incremental innovation in terms of adding more capacity, adding more lines, adding more automation to the voice network gets totally revamped as technology changes and experiences a fundamental change as voice over IP rolls out. And so the case I'm trying to make here is that these incremental innovation cycles occur time and time again until you have a period of fundamental technological change. And I think we're about to have that happen in the network intradomain space. In the network interdomain space. So for the rest of this talk, I'm going to give some thoughts about what's happening in the intradomain at the sort of the layer 1 through 2 area of the network. What's going on in the application domain, layer 5 through 7. And I'm going to make the case that we're missing something in the layer 3 domain, or the network interdomain between networks that are interconnecting to one another. So let's just look at history of where IP routing has gone. We started off with basic hop-by-hop routing, box-to-box forwarding. We moved on to a time and period where one box started to rule them all. We had the BFR, similar to the crossbar switches where we had common control and a line card architecture, up to today's distributed architectures, similar to the talk we saw yesterday about distributed supernodes, where we can think of individual chassis as a line card and a matrix router, up to this notion of the last 10 years, fundamental technological change occurring in the advent of software-defined networking that many of us use to drive our networks today. So, we have an evolution in routing, and at the same time, we have an evolution in the underlying technology where, just a few weeks ago, we saw an announcement for Broadcom's Tomahawk 4 processor. We now take, 25.6 terabit of switching capacity, drop it into a 2RU chassis for under 1,500 watts of power consumption. Whereas, just the previous generation, 12.4 terabit per switch chip, or 12.8 terabit per switch chip, we need 6 of them, probably drawing around 3,000 watts for the same switching capacity, probably 4RU of rack space. All of this is iterating and compressing down. Now, the advent of SDN has allowed us to massively instrument our local networks far more than we've ever seen before. And what I believe here is that this is giving us the prevalence of single-sided intelligence in the network, meaning that either as a content operator or as an edge cloud operator or as a hosting provider, we can see a lot more of what's going on in the network, but there is still a blind spot in the interdomain space. We get some viewpoints due to absorbing telemetry data from clients directly via an out-of-band channel connection across the internet, but we still don't necessarily know what's going on in that third-party network. So let me give that to you visually. Traditionally, a content host would run their own data center, or they would run their content hosting somewhere in the world. Maybe their internet connection would come from the data center itself or from an ISP. We've seen that construct evolve as content providers got into the business of being their very own ISPs and connecting much closer to the core of the internet. We can see that we get telemetry coming in from users directly or from clients directly, so that way we can see what that user experience looks like. But at the end of the day, the third-party network, the last mile or the middle mile that we're transiting through, is not necessarily participating in that transaction. We don't necessarily have visibility there. We can't find out what's going on in the network. We don't have any points of introspection or telemetry coming our way. And so what that means for content providers is that we're constantly pursuing the edge of the network. We're trying to go deeper and closer to the users to understand what's happening in the network, so that way we can make for the best possible experience that we can give them. And sometimes that might mean that the content or the host is going to build far more deeply into the network than we've historically seen. And what we're trying to deal with here is we're trying to cut down on the amount of interdomain information asymmetry that exists, right? And this concept of information asymmetry goes back to managerial economics and business strategy, right? For a market to function efficiently, participants must have reasonably good information from all sides, right? And that, in our world, in the world of networking, that can be about interconnection, network conditions, patterns of congestion, day-to-day usage patterns. And without having that information from both sides, there's a number of inefficiencies that occur in the system. So, I would agree that anyone knows their network, their own network, better than anyone else. And that comes from their policy, economics, constraints, and preferences. But my question is with that network piece not being part of the transaction, is there an opportunity to open that information up? And I have a few more words on that later. So let me flip from sort of the physical network piece and go up the protocol stack to what's going on in the HTTP world, because I think that this is an important consideration as we move ahead. If we look at the history of HTTP, similar to what we see with interdomain routing, similar to what we see with data center fabrics and switch chips, we see an evolution, right? In 1991, we have HTTP 0.9 ratified by RFC as the one-line HTTP protocol. RFC 1945 comes along in 1996, which gives us HTTP 1.0. So we get things like versioning and status codes and headers and content types in the protocol. And then really nothing happens for a while until 2014, 2015, where we see updated specifications for HTTP 1.1 come out, as well as RFC 7540 defining HTTP 2. And HTTP 2 takes an incremental approach at improving the protocol, primarily so we can eliminate head-of-line blocking in HTTP. So we now get a protocol that provides multiplexed binary encoding on the wire, provides for header compression, something called server push, more on that later, as well as HTTP alternative services. And get ready, because in 2020, we're expecting the newest version of HTTP, HTTP 3, to come out and start being used live on the web. And that's available to you today. So if you go to http3.is, you can see a demo site of HTTP 3. Now, on the left-hand side on my laptop, I just have regular old Chrome running, and HTTP 3 does not get used. But if you go grab the Chrome nightly build, the Chrome Canary build, and throw these flags, -- enable quick and -- quick - version H327, and use the Chrome Canary and hit http3.is, you will see a demonstration of HTTP 3. And I want to tell you a little bit more about what's going on with HTTP 3, because I think it's important in thinking about how we manage networks in the future. So as I said, it's the upcoming version of the Hypertext Transfer Protocol. It has feature parity from HTTP 2, but unlike HTTP 2, which is carried over TCP, HTTP 3 is carried over QUIC, which is a brand new transport protocol. So just some reminders. HTTP 2 functions over TCP. So while HTTP 2 fixes the head-of-line blocking problems associated with HTTP 1.1, we still have issues with head-of-line blocking in the TCP protocol itself. And that's what we're trying to address with HTTP 3. The other thing that's very interesting about HTTP2 is that it implements something called HTTP alternative services. HTTP2 connections are meant to be very, very long-lived. And so therefore, as you're trying to do traffic engineering in the network, you have a couple different problems. Traditional load balancing and global server load balancing, traffic engineering techniques today really sort of boil down to one of two things. BGP Anycast, which for a long-lived connection, if you move those endpoints around, you're going to break the connection on behalf of the user and degrade the user experience. Or you're going to use some sort of DNS-based GSLB system, which requires new lookups, which requires those connections to get restarted, and therefore you're not going to have the same traffic engineering control of the network as you may have had at the HTTP layer in the past. So HTTP alternative services exists as a way for a server to notify a client of an alternative URI to fetch the same content from. And there was some investigation into the security of that. It looks like there was some misguided implementations of how this is supposed to work. That's being fixed, but fundamentally this technology works. So we now have a means to control how clients are connecting to server endpoints in-band to the HTTP protocol itself. We don't have to use the DNS. We don't have to use BGP Anycast for this anymore. And that's all available in HTTP 3. Adding to the complexity of this, HTTP 3 is not carried over TCP. It uses a new transport protocol known as QUIC, which is actually carried over UDP. And the designers of the QUIC protocol and the HTTP3 protocol use QUIC because it resolves the head-of-line blocking issue in TCP. The other thing to take away from this is that connections in QUIC are not defined by the traditional 5-tuple that we're used to. There are connection identifiers in the QUIC header that are actually used to identify client and server connections. The other thing to note is that much more of the payload in QUIC is natively encrypted using TLS 1.3. So as network operators, there's a lot less inspection that we're going to be able to do in the network. More on that in a few seconds. Now, the parameters for mobility in QUIC changed dramatically. As I said, we now have HTTP alternative services to help move clients to different server endpoints. But what's interesting about that is not only can we move server endpoints around, similar to a direct server return like connection management on the serving side, we can also move the client connection around in a stateful manner on the client side. So we serve one of QUIC's goals is to serve what they call the parking lot problem, where you're leaving your office at the end of the day. Your mobile device hasn't transitioned off of your Wi-Fi to get onto the LTE network. The connection gets interrupted. In QUIC, that connection can be seamlessly migrated from a UDP endpoint on the wireless LAN to a UDP endpoint on the LTE network. And we can, again, use HTTP alternative services to move the server location around depending upon local network conditions. So, with all of this mobility, both client-side, server-side, we can imagine what the future of things like Kubernetes containers deployed along the network or serverless functions at the edge can do for us, where now when I want to get to my user and maybe my core data center isn't the most optimal serving site, I might move that workload to a new UDP endpoint far deeper into the network than I had before. And this happens seamlessly to the user. It can happen seamlessly to the user. And that means fundamental changes for network operators are going to occur. The middle boxes that we're all used to having in our networks, whether it be for NAT or for firewall or for content inspection, really can't touch the QUIC protocol the way that we've seen the TCP HTTP protocol get touched. Interference with the payload of any sort results in a connection reset, and the user will know that something happened to their connection. We're now seeing that routing protocol decisions in some ways are moving up into the application protocol stack through HTTP alternative services. And if you watched Paul Vixie's talk from a couple nanogs ago, we're looking at we're investigating the DNS lookups moving alongside the HTTP traffic. And so we can plan on having much more localized effects of, well, my internet doesn't look like your internet anymore, and what's going on here. And what that means for operators is reduced observability, less traffic classification, and perhaps less opportunity to create value in the network. If you're a network operator and you want to study up deeper on what's going on with Quick, I would suggest reading this IETF draft for Quick manageability. It's currently at version 6 as to what these fundamental changes look like for network operators in detail. So we have these massive innovations occurring at the intradomain level and at the application domain level. And I want to acknowledge what's going on with RPKI in the interdomain space, but I still think that there's an opportunity here. And as network operators, we're missing something. What I'm trying to say is that the remote infrastructure that serves the client from the perspective of the serving stack is just not a piece of the equation yet. As content operators, we've been able to bring together the application layer, the serving stack infrastructure, and the physical and logical layer. But what's going on in that remote network is really still quite opaque to us. And so that remote network is very much disconnected from what developers can do today. Developers can do way more with the network than they did 10 years ago. They can write more client code than ever before. Companies that are responsible for running their own serving stack as well as their own client stack under a common mission can control all these aspects and really relay on very, very rich telemetry as to what the user experience is. I mean, I'm always thinking about what the Netflix folks can do because they control the serving stack deeply, the control plane for their application stack as well as the client stack in a very native and common way. So they can align those missions. We never used to be able to see that with browser technology because we always had a third-party client. But with the advent of the app ecosystem, that changes dramatically. With HTTP3 and alternative services, we're starting to get some of that functionality right into the native browser. And so, what I believe is that developers are doing a lot more guessgineering, in quotes, about what's going on in the network to try and find out conditions of the network in real time. And that leads to a lot of inefficiencies in how we operate networks. One thing that's very interesting about Quick, and the Quick authors wanted to have the capability for, is to iterate faster in this network stack. They wanted developers to be able to think about future improvements to this network stack in a rapid manner. And so what's interesting is that the initial implementations of Quick are actually user space implementations. So the way that you get a Quick process up and running is you take your serving software and you bolt on a module so that way you can understand the Quick transport protocol and then go bind that to a UDP socket. So by deploying that software in user space, you can iterate on what that software is doing far more rapidly. What I want to get across here is that sharing information does not mean that you're giving away control of your network. And so I think that there are opportunities using technology that we have access to today to share information in between networks that ultimately benefit all of our collective users. So one example of that is, can we do some more suggestive signaling in the network using something like BGP large communities? If I'm peering with another network, can that network signal to me some alternative paths in the network where if that peering link should saturate or congest, how does that eyeball network want to receive overflow traffic? And, I have some example communities that I wrote up that, someone like an AT&T could use to signal that to content operators. Or perhaps there's congestion in a particular metro market and we need to shift traffic completely elsewhere. Or as a content provider where we are exposing different VIPs to the internet and different IP blocks, perhaps we can provide some signaling to network operators about the type of traffic that's being carried on those blocks. So that way we can be smart about managing congestion. Or can we use BGP large communities to signal readiness for bilateral session establishment across IX route servers. So that way then software and automation can come and set up bilateral sessions rather than trading emails between human beings or scraping down various internet peering databases and using a spray and pray type method. I believe that information drives simplicity in the network. And if we can make the networks more simple, then we can actually significantly reduce waste. We can stop over provisioning networks because we don't know the best path. We don't have to guess about what the best path is through the network anymore. Maybe we can move workloads based upon prevailing network conditions or historical network conditions. With Quick, if we can sort of move the client around and move the server around seamlessly without resetting connections for the user, that gives us much more mobility of where we serve those workloads from. And maybe we can reduce significant amounts of human energy that's spent debugging, reconfiguring, and engineering to find IO paths through the network when computers can do it anyways. We figured out how to do this in the network intradomain with software-defined networking. So how can we extend that across network boundaries, across autonomous system boundaries in the future? Now, I think I'm going to get a lot of objections to this because, we've heard some of these before, like things like, well, my network topology and the conditions on my network are my competitive edge. But I think that telemetry data coming from clients is already telling content operators about that. Or maybe my router can't run more processes in its control plane. But I think we've learned that from software-defined networking and the deployment of RPKI, we know how to sideload data into the network. We can process large maps, we can process vast amounts of information, and then really load only into the forwarding plane what we need to implement the desired state that we're looking for in the network. Or you might say that I'm, reducing the network to being the last common denominator, but what I'm actually looking for is the most efficient allocation of resources. Or you might say, sharing this information allows for network arbitrage. I would argue that it's already happening. So I think that there's a whole another round of innovation that can occur in how we operate networks. We're seeing a lot of innovation down in the physical layer in SDN. We have innovation going on in the application domain, and I think that there is something missing in the interdomain. The interdomain has had a rich history. The NANOG group has been evolving this for a long time. It goes all the way back to the late 90s with the advent of NAPS and PeeringDB, the Global Peering Forum. But I think that there's more that we can do. There's enhanced signaling that we can deploy between networks. There's session creation automation that we can look into. There's flow information sharing that can go on between networks. There's some great work around something called DOTS, which is a DDoS situational awareness protocol between DDoS mitigation appliances on-prem and the cloud. And then we can look at the advent of edge compute, serverless functions, containerized workloads to think about how we move workloads around the internet dynamically to coordinate for better end user experiences. And I think once we can get to that state, then we can realize a place where the application layer, the local infrastructure serving stack, the remote client infrastructure stack, as well as the physical layer is brought together in a harmonious fashion, and the network will be far more efficient. That's my take on some ideas for the future, and I would love to take any questions that may have popped up along the way. Feel free to shoot me email with complaints or suggestions as well. tjd@q7.io is the email address. Thank you for this time.